What's up, everybody? It's Dustin from DP Alternative Energy Designs, a not-for-profit organization dedicated to alternative fuel technologies. What we have here today is the beginnings of our recumbent electric bicycle project. We have some round and square tube aluminum material that I picked up at our local scrapyard. Got a couple of aluminum lawn chairs. And we have a couple of Huffy Black Widow 21 speed dual disc brake fully suspended mountain bikes, and a couple of junk bikes, mountain bikes that I had hanging around that I picked up here and there over the years. And this pile of metal and junk and parts with a welder and a grinder. And some measuring tools is going to transform itself with a lot of hard work into a two-seater recumbent electric bike with solar recharging capability, as well as hydrogen augmentation and an onboard electric generator. Probably going to be biodiesel or ethanol fueled genset. And what this is going to be is a small-scale representation of the H2 EV Air project, which basically encapsulates the concepts of an onboard electric generator with electric propulsion. We're going to prove the concept that the combination of technologies is feasible. We are going to use the batteries out of a Prius. What we're basically trying to prove is that a genset running at a constant RPM will get better fuel economy than an internal combustion engine used as a prime mover. To cope these tubular joints together and mock them up prior to welding, what I do is I've created a system. It's the poor man's coping jig. You can do it with a drill press and a circular cutter, such as something along the lines of these cutters. And I did do some of my coping with these cutters. They leave a pretty rough finish. And you really have to hold the jig really tightly in the drill press. Once I get the angle and the curve that I want for a nice cope fit, once I get it, pretty close to the way I want it, what I do after I fit one end is I wrap a piece of paper and tape along the coped end, and I make a template such as this right here. And then all I have to do is flip it over for the other end of the tube, and what I have is an exact recreation of the proper fitting cope on the other side of the tube. So then all I have to do is scribe out the lines, and then with a hand grinder and some files, I shape according to the marks that I've made. I'll make those with a magic marker, just scribe right along there. And that's pretty much how I've been joining my tubes together. Here we've got some coped joints here. You can see where I've been joining these tubes together and getting them to fit tightly so we get good welds without a lot of gaps, because gaps end up creating really fat welds, and you end up having a hard time controlling your puddle because you're trying to bridge an air gap in the tubing. and you end up with super wide welds, and you end up melting the edges of your tube. So if you want to get them tight as you can, this one's pretty good. There's a small gap in there, but nothing that can't be overcome. So that's how I've been fabbing up and welding the tube frame for this electric bike. To create a steering linkage rod such as this, the first thing that I do is I cut a small disc of aluminum that is just over the OD of the tube, so that there's a little bit of overlap. And what I use that overlap for is when I weld, I melt the puddle down over the side, and the result is the disc welded to the end of the tube, and then I drill and tap a hole right through the center of it, and that's how I make the linkage end, and the rod simply inserts into this end here. Now I have assembled the rod ends and connected all the steering to the linkages that I fabricated. You can see I modified this handlebar and this part of another bike frame that I welded onto my existing frame. Okay, and that acts as our steering post mount. So you can see my rod ends. I've got 4 of them. Okay, and you can see the tie-in linkage here for the opposite wheel. So the main control is on the left wheel, since it is a left-hand drive vehicle. And this is basically how the steering works. It's pretty slick, as you can see. Steers pretty much like a normal bicycle, since it has all bicycle parts in it, except on this you won't be leaning, obviously, because it'll steer like a car. But the hand grips and all the controls will act as a normal bicycle would. So technically it's still retaining that bicycle feel. And you can see the steering is really, actually it's pretty precise, for the reason that these rod ends that I use, they're brass inserts. They're real tight, so there's no play in these rod ends at all. A single motion with your hand is directly translated to the wheel with no play at all. No fancy gears or no rack and pinion. I just decided to use regular old pulley levers and fulcrum points, and it works out real nice. And the only thing I have left to do now is I got to build some stops. Progress with the traction drive system. Here you can see the golden motor, in-wheel, 26-inch hub motor. This is a brushless DC, 48-volt design, 1000 watt, with an integrated disc brake and 7-gear sprocket set. And of course we have 2 wheels, so we have identical setups on each side with disc brakes. So the way these derailleurs are activated, I have a cable that runs from the handlebars right down through here, goes to this 90-degree elbow and into this frame gap here, where I have a 2-into-1 block, tie-in block, which basically converts the pulling force of the single cable up from the handlebars and splits it off into these 2 cables here to actuate both derailleurs. And that cable runs along the frame, along with the disc brake cable, runs along the side of the frame here, and up to the handlebars, and the shifter here. And this is our actuation. Now, this actuation is a lot stiffer than a normal bike shifter would be, because of the fact that you have two derailleurs and spring tensions acting against it. So I may rig up a counter spring on this to relieve some of that pressure. But it works nonetheless, even though it's a little stiff. It does work to shift appropriately. So you can see the Golden Motor brake handles with the integrated brake light. That also shuts off the cruise control. So I've got those hooked up on a splitter in much the same way. You can see them both operating there. And those split off right down here below my shifter split off. This setup here for the rear brakes is a lot like an e-brake system for a GM. Well, it's similar to what's on my Oldsmobile. So that style, millions of GM cars were built with this kind of a configuration where you have two e-brake cables. In this case, they'd be the normal bike cables, but there's a mid tie-in point right here where the cable comes in. So when this cable pulls on that block, first it pulls these two together, and then when this side brake fully engages and comes to a stop, and there's more travel left, it begins to pull on this side and engage this brake here on this side, and they engage simultaneously pretty much. You can't really feel the difference between the two. It's very effective. So I've started the wiring on the Golden Motor traction drive system. You can see I've got some of this wiring done up here for the controllers. And here is one controller for one motor, and the other controller is on the other side. I mounted brackets here, welded in some brackets for these two controllers. I mean, they're pretty small. It's pretty cool. The actual drive system, if you don't count the batteries, is this and the throttle lever. I mean, it's really cool how tight and compact it is. Here you can see the Prius battery, how it's mounted in place at the bottom of the bike. You can see all the fabrication that was done there. And here on the side, you can see how the Prius battery has been reconfigured for 4 48-volt cells, and that's just a matter of changing these jumpers around. You disassemble the battery, change the jumpers around. Of course, when you first grab a Prius battery, it's over 200 volts, so you always have to use extreme caution. Now, of course, it's a little safer. The voltage is a lot lower. Same thing on the front, the other side of the battery. Jumpers are reconfigured for 48 volts. I'm in the process of wiring all this up right now, so it's not quite finished yet. After I get done with the wiring, we'll do a test run. So you've seen the steering in a previous clip, and this is the handlebar setup. I've got a speed, an odometer and speed indicator and trip meter here. And here are some of the various functions. You get obviously a horn. These are for lights. On the other side of the controller, you've got your battery indicators, and this could be a reverse button. And this is a thumb throttle, which I found a little bit more convenient than a twist throttle, especially on this vehicle. If you're going over some rough terrain, the twist throttle might be a little more challenging than the thumb throttle. So, and this is the bracing for the steering bar that I made up. Stiffens up the frame, keeps the handlebars nice and stiff, keeps the steering nice and tight. And here's the splitter. This is the splitter mechanism up here. It's very similar to the shifter splitter for the front brakes, except I have some pivot points here, and you can see the cable run down. And I've got bigger disc brakes on the front than in the back. I got these off of electric bike that Larry Jarbeau donated to me. And that bike had some electrical issues that couldn't be repaired effectively, so it's getting a second life as part of this project. As you can see, I haven't finished the crank. Big empty hole there. The crank assembly will be one of the last things that I complete because I'm still waiting on some parts, so I'm working on this other stuff right now. going?
I'm trying to.
Yeah, the pedals. I don't have pedals on it yet, so.
Oh, my legs are not as long as yours.
This is the battery and battery management system on the EV recumbent bike. So we have a Prius battery that has been reconfigured to 48 volts by reconfiguring the posts. So what we have are 4 banks, 1, 2, 3, and 4. Banks of 48 volt DC nickel metal hydride battery packs. For each battery pack, we have a battery charger. The battery charger is a smart charger. They have temperature probes. They also sense current and voltage and are designed to properly charge the nickel metal hydride and meet the needs of those type of technologies. So the issue is, when trying to charge a large battery pack like this as one unit, each section has its own dedicated battery charger. There's 2 over here, and there's 2 over here. Now, the issue with that, of course, is that the traction drive system, which actually consists of these 2 wheel hub motors, which are controlled by these controllers using the same signal. So, in order to tie in the 4 banks into these 2 controllers, I decided to use a relay bank. When it's closed and the contacts are activated, it essentially ties all 4 of these batteries and treats them as one 48 volt module, which is not possible to use the battery management system of the 4 battery chargers. So what this does is it disconnects the outlet to the controllers, which ultimately go to the motors. When you have this switch here controls the traction control system, so when it's in the on position, all of the relays are activated and the vehicle will move. This red switch here turns the controllers on, and you have an indicator here that shows when the controllers are on or off. So now the controllers are on, but when you hit the thumb throttle, nothing happens. And that is because these relays have not been energized, so they are not allowing power to be routed back here to the motors. So what you do is you turn on the relay bank. Now the relay bank is on and the bike will move. Okay? So by disabling the traction drive system and disconnecting the batteries from the motors, you now essentially have 4 separate battery banks completely independent of each other that can be run off 4 separate smart battery chargers. And the power cords to those chargers, I have all those power cords tied in right here into this one box with one outlet in it, just like that. So you plug that in, and all 4 chargers work in unison and separately charge all the 4 banks. That is a affordable way. It's about $200 in battery charges versus several hundred more dollars for a smart charging computerized system, which serves the same purpose. And like I said, it's temperature monitoring. The nickel metal hydride batteries need to be monitored for temperature when they're being charged. So that is the most efficient way, and the most inexpensive way and effective way to utilize battery banks that are wired in parallel and have an onboard charging system that will function. And the recharge time on these batteries will be about 4 hours. So, and that's not too bad for an entire Prius battery bank. So we've yet to do, obviously, we haven't even done the maiden voyage. We're about to throw the sheet on this and do a maiden voyage, and we have no idea what the range is going to be. So, you know, we're going to have to figure that out. We're going to have to go out and take a run. We do have a trip meter here that's going to give us our speed and distance, and then we'll be able to calculate our range and amount of power used so that we can then start to size out the genset that we're going to need once we remove this battery pack, which is temporary. In the future, this battery bank will be replaced with a capacitor bank, and behind here will be a small genset rated properly for the power demands of this vehicle, and we will move forward with the cap drive system, an electric vehicle with an onboard genset and no batteries, the precursor to the H2 EV Air prototype project.